We begin our journey at the absolute boundary of a proximal tubule epithelial cell, the apical plasma membrane. Just outside this lipid bilayer is the luminal fluid. This is a continuous, high-volume environment rushing past the cell, densely packed with dissolved solutes. The defining characteristic of this extracellular space is its high concentration of sodium ions. Inside the cell, in the cytosol, sodium is heavily depleted, creating a severe physical imbalance across the membrane. This imbalance exerts a steep, persistent electrochemical gradient, a literal downward force pressing those extracellular sodium ions toward the interior of the cell. Scattered among this sea of sodium are molecules of glucose, which exist in much lower concentrations. To prevent the loss of this vital fuel source, the cell must capture these rare glucose molecules and pull them inside. Moving a molecule against its local concentration gradient is an energetically unfavorable task. Without an external source of work, the system cannot overcome the entropy of the gradient to achieve net transport into the cell. The cell solves this problem by using the environment it has already dealt. The massive reservoir of stored potential energy within the sodium gradient provides the exact thermodynamic force needed to drive the otherwise impossible reabsorption of glucose. The structure responsible for capturing and transferring that energy is the sodium-glucose cotransporter 2, or SGLT2. SGLT2 is a multi-pass integral membrane protein embedded directly within the apical boundary. It is constructed from a single continuous polypeptide chain that weaves back and forth across the lipid bilayer. Because the interior of the lipid bilayer lacks water, the chemical bonds along this chain are forced to interact. This physical constraint causes the spanning segments to twist into tight spirals. These specific spiral structures are known as transmembrane alpha helices. Rather than sitting flat in a row, these individual alpha helices cluster together, forming a distinct cylindrical shape right through the hydrophobic core of the membrane. This exact alpha helical barrel architecture creates a highly specific, strictly regulated channel bridging the luminal fluid to the cytosol. SGLT2 operates as a secondary active transporter, specifically functioning as a symporter. It does not feature a catalytic door its mechanical movements. Instead, the protein relies entirely on the steep sodium electrochemical gradient pressing against the exterior of the cell. The thermodynamic coupling works like a mechanical gear system. The spontaneous, highly favorable influx of sodium into the cell provides the active kinetic driving force. As that free energy is released, it is directly transferred to power the non-spontaneous transport of a single glucose molecule. This diagram shows an intestinal epithelial cell, demonstrating a highly similar process. In the apical domain, the sodium ion and glucose molecule are moved in the exact same direction across the membrane, defining the symport mechanism. This entire process is strictly dependent on the basal conditions of the cell. If the sodium gradient is not maintained by the cell's internal pumps, glucose transport immediately ceases. By acting as a thermodynamic bridge, secondary active symport couples an energetically favorable reaction to an unfavorable one, ensuring continuous capture of essential cellular fuel. At rest, SGLT2 sits outward open, leaving its binding pocket exposed to the luminal fluid. The kinetic cycle begins when a single luminal sodium ion drops into this pocket and binds to its specific structural niche. The arrival of the positive charge triggers a rapid allosteric shift in the protein. The adjacent physical space changes shape, drastically increasing its binding affinity for glucose. A passing luminal glucose molecule then docks perfectly into this newly optimized site. Holding both substrates at once makes the outward open structural state highly unstable. The protein resolves this instability through motion. The internal alpha helices rapidly slide and pivot against one another, collapsing the outward face while dilating the inward face. Once exposed to the intracellular space, the sodium ion and glucose molecule detach and diffuse away. Empty once again, the protein snaps back to its baseline, outward open position. This continuous, high-frequency ping-pong oscillation is the primary kinetic mechanism of alternating access transport. The system changes when the pharmacological agent dapagliflozin is introduced into the dense luminal fluid. Dapagliflozin operates as a high-affinity competitive inhibitor. engineered to target the outward open conformation of SGLT2. Once the allostoic site is prepped by sodium, dapagliflozin enters the glucose binding pocket, actively beating the native glucose molecules to the space. Notice the strict linear arrangements of hydrogen bonds. Dapagliflozin uses this mechanism, aligning perfectly with internal residues. The van der Waals forces curve shows how dapagliflozin's topography matches the pocket, maximizing atomic attraction up to the optimal distance without repulsion. This diagram demonstrates how weak chemical bonds provide tight binding when many are formed simultaneously. Through high complementarity surfaces, dapagliflozin utilizes these meticulously calibrated non-covalent forces to lock itself deeply into the target pocket. While native glucose relies on a similar set of non-covalent forces, the chemical architecture of dapagliflozin allows for a much larger number of simultaneous interactions. This results in a binding affinity several orders of magnitude stronger than that of the native substrate. By exploiting this optimized biophysical geometry, the drug monopolizes the active site, entirely precluding native substrate from docking. Dapagliflozin carries a distinct structural anomaly when compared to glucose, a large, bulky aglycone tail that extends outward from the primary binding pocket. As the protein attempts to execute its standard kinetic cycle, this massive molecular structure physically collides with the dense walls of the surrounding alpha helices. This intense physical obstruction is known as steric hindrance. The bulky tail acts as a rigid wedge. It occupies too much three-dimensional space, physically preventing the alpha helices from executing the sliding and pivoting motions required to close the outward face. The entire alternating access cycle reaches a kinetic standstill. SGLT2 is locked permanently in its outward open conformation, effectively removed from the transport pool. The massive thermodynamic potential of the sodium gradient is still there, pressing against the membrane, but the mechanical engine designed to harness it has been neutralized. Out in the luminal fluid, unbound glucose molecules are systematically rejected by the locked receptors, causing their concentration to rapidly surge. By imposing absolute steric arrest on a single conformational hinge, dapagliflozin overrides the baseline thermodynamic drive of the cell, forcing the continuous luminal accumulation and eventual physiological excretion of glucose.